Sorry about that. Someone was knocking at my door. As I was saying, I need to be careful with this logarithm function because it's not defined at x equals 0. It's got a vertical asymptote. So with that in mind, I'm not going to do a Maclaurin series for just the natural logarithm. I'm going to do a Maclaurin series for the function the natural log of the quantity x plus 1, or 1 plus x. Order of addition doesn't matter. So again, the number 0 derivative, if I've taken 0 derivatives, then I have not changed the function I've got. That'll be natural log of 1 plus x. When I take my first derivative, I know that the derivative of the natural log function is 1 divided by the argument. So here, 1 divided by 1 plus x. Then I need to multiply by the derivative of the quantity inside, right? This is the chain rule. But like in my previous example, that's just going to be the number 1. Now, I'm going to slightly rewrite this formula just to make the next couple derivatives easier to work with. Because 1 plus x is the denominator of my fraction, I will say this is the quantity 1 plus x raised to the power minus 1. What that lets me do is now I can immediately say that the derivative of this thing is going to be minus 1 plus x. I need to reduce the exponent by 1, so I'll get the negative 2 power. And then chain rule says multiply by the derivative of the inside, which is still just positive 1. Okay, one more derivative and I'll be all set. I need to bring down the exponent minus 2, so I'll have positive 2. 1 plus x now to the power minus 3, and multiply by the derivative of the inside, which I know is positive 1. So here are my 4 calculations, my derivatives. The original function, its first derivative, its second derivative, and its third derivative. Now I'm going to evaluate these things at x equals 0. So if x equals 0, I'll have the natural logarithm of the number 1, which is just 0. For n equals 1, if x equals 0, I'll have just the number 1. For n equals 2, I'll have the number minus 1 times 1 to the power minus 2. But 1 to any power is still just 1, so that'll simplify nicely. And for n equals 3, I'll have the number 2. Now, when I put these into my Maclaurin series formula, that tells me that my constant term is going to be 0. My linear term is going to be 1 times x. My quadratic term is going to be minus 1 times x squared. And my cubic term is going to be positive 2 times x cubed. So here are the first 4 terms of my Maclaurin series. Because I'm doing a whole bunch of these, you'll notice that I'm not doing the simplifying steps as frequently in my last column here. In my mind, it's a pretty straightforward thing to calculate once I've set up the table here. Really, the only thing that changes is just the calculation of the successive derivatives. The rest of the work is just plugging in values of x with the occasional simplification. Let's look at another function. Now I want 1 plus 2x. I'm going to raise this whole quantity to the power 3. So here we see some non-trivial chain rule. Once again, the 0th derivative of the function is just itself. I have differentiated 0 times. As I take higher derivatives, I will be using the power rule. So the first derivative of this function is going to be 3 times 1 plus 2x, all to the power 2. And now I need to multiply by the derivative of 1 plus 2x, which I know is 2. So altogether, you might call this 6 times the quantity 1 plus 2x squared. Let's keep going. I want to take another derivative. I know that when I take derivatives, constant multiples just come along for the ride. So I can use my power rule again and say, I'm going to bring down the exponent. Now I've got a leading coefficient of 6. I have the quantity 1 plus 2x. This is now raised to the power 1. And finally, I need to multiply by this 2 that came from the previous line. Constant multiples come for the ride. But I've also got to multiply by another power of 2. Again, for the chain rule. So this time my derivative is 6 times the polynomial 1 plus 2x times the number 2 squared. I'll do one more derivative. So I'll have 6. Now I've got 1 plus 2x to the power 0, right? I'm bringing the 1 down. 1 times 6 is still 6. And then raising this polynomial to the power 0 gives me just the number 1. I need to multiply by this 2 squared. That comes along for the ride. And I need to multiply by another power of 2 for the chain rule. So now I've got 6 times 2 cubed. So here are my successive derivatives. Now I'm going to evaluate at x equals 0. For this first number, if x equals 0, I'll have 1 cubed, which is just 1. For n equals 1, in the parentheses, I'll have just 1, and I square it, and then I multiply by 3 and by 2. That's going to simplify down to just 6. For the next line down, x is 0, and this expression is going to simplify to 24. And then for the third line, the number 3 line, I should say, this will simplify down to 48. So now these are the numbers that I'll use in my Maclaurin series formula. My constant term will just be 1. My linear term will be 6x. My quadratic term is going to be 24 divided by 2. My numerator is 24. My denominator is 2 factorial, which is just 2. And that's going to simplify to 12x squared. And then finally, my cubic term is going to be 48 divided by 3 factorial. That's the coefficient. 3 factorial is the number 6. 48 divided by 6 is 8. Like so. So the first 4 terms of my Maclaurin series are constant term 1, linear term 6x, quadratic term 12x squared, and cubic term 8x cubed. If I kept going, if I wanted the quartic term or the quintic term and so on, well, at n equals 3, my function's just a constant. So at n equals 4, the function, my derivative is just going to be 0. And n equals 5, my derivative is just going to be 0, and so on. So I'll just get zeros for the rest of the terms in this series. And that should make sense because I could have just FOILed out this polynomial. It's to the 3rd power, but that's not impossible to work with. And what would that have gotten me? Well, it would have gotten me 1 plus 6x plus 12x squared plus 8x cubed. The Maclaurin series is supposed to be agreeing with the formula that I started out with. And for polynomials, like this polynomial, the Maclaurin series will agree exactly with whatever the polynomial would look like written out as powers of x. I think that's really cool. So we use derivatives here to expand this out without necessarily doing all the multiplication. Let's look at one that's not a polynomial. So this time I want the function where I take the number 2 plus x, and I raise this to the power 3.3. So this is similar, but it is different because I'm not looking at a whole power. So this does not count as a polynomial anymore because of the power 3.3. Well, at this point, it should feel a little comfortable. The 0th derivative of this function is itself. The first derivative, well, I'll be using the power rule again. I'll bring down the 3.3. Now I've got 2 plus x raised to the power 2.3. And the derivative of the stuff inside is just going to be 1. So I would have to use the chain rule here. Chain rule says multiply by positive 1. Not a big deal. To continue differentiating, the second derivative is going to be 3.3 times the number 2.3 times the quantity 2 plus x, which has been raised to the 1.3 power. And then for my third derivative, I've got 3.3 times 2.3 times 1.3 times 2 plus x raised to the power 0.3. Okay. Again, I'm going to evaluate these things at x equals 0. For this demonstration, I am choosing to leave these in the formula that they've been given to me. Depending on what your application is, it might be more useful to find decimal approximations of these numbers. So for x equals 0, the stuff in parentheses is just going to be the number 2. And there's not really a whole lot of simplification I could make here. For n equals 0, I'll get the number 2 raised to the 3.3 power. For n equals 1, I'll get 3.3 times 2 raised to the 2.3 power. Again, sorry for the mouse handwriting. For n equals 2, I'll get 3.3 times 2.3 times the number 2 raised to the 1.3 power. And for n equals 3, I'll get 3.3 times 2.3 times 1.3 times 2 to the 0.3 power. Now, each of these will be the numerators for my Maclaurin series terms. The denominators are the factorial numbers. 0 factorial is equal to 1. 1 factorial is also equal to 1. So for my constant term, I'll get 2 to the power 3.3. For my linear term, I'll get 3.3 times 2 raised to the 2.3 power times x. For my quadratic term, I will get 3.3 times 2.3 times the number 2 to the 1.3 power, all divided by 2. And this is raised to the power x, this is multiplied by x cubed. And for the very last of these, I'm a bit short on space, but I'll get 3.3 times 2.3 times 1.3 times 2 to the power 0.3. This will all be divided by the number 3 factorial, which is equal to 6. And this is times x cubed. And I see one typo on here. Of course, the quadratic term is what I get for x squared. Sorry about that. Now, I have one more example that I'd like to go through. This one was a little bit complicated because my power here ended up being a bit of a mess. Without resorting to decimal approximation, the formula is just getting longer for each line of the table. So let's move to something that won't have that same issue. Let me just clear all of this. I would like to look at the function cosine of 2x. Just a minute here. There we go. So my function is cosine of 2x. I want to find my Maclaurin series. Well, I need to calculate some derivatives here. Of course, the original function is cosine of 2x. And then as I take derivatives, I do need to use the chain rule. So my first derivative is going to be 2 times minus sine of x. That'll be sine of 2x, right? So the derivative of the cosine function is minus the sine function. I keep the arguments of these functions the same, and I multiply by the derivative of that argument, the derivative of the inside function. Okay. Well, if I take a second derivative here, derivative of the sine function is the cosine function. The inside piece stays the same. That'll be my 2x. The negative 2 comes along for the ride because that's a constant multiple. But I do need to multiply by an additional power of 2 because of the chain rule. That's the derivative of the inside here. And now one more derivative. Derivative of the cosine will be negative sine. So that will bring me back to positive. The argument here will be 2x, And now the coefficient will be positive 8. All right, there are some derivatives. When I go to evaluate these functions at x equals 0, well, I'll be doubling this x, but twice 0 is still 0. So this first number that I get here for n equals 0, cosine of 0 is the number 1. For n equals 1, I'll have sine of 0, which is 0, multiplied by negative 2. But that's still 0. For n equals 2, I'll get negative 4 times cosine of 0. Cosine of 0 is 1. Then for n equals 3, I'll get 8 times sine of 0, which is 0. All right. So that means that the constant term of my Maclaurin series is the number 1. My linear term of the Maclaurin series is the number 0 divided by 1 factorial times x, or just 0x. My quadratic term is going to be minus 4 divided by 2 factorial. So I'll call that minus 2. That's the coefficient of x squared. And then for my cubic term, I will have 0 times x cubed. Those are the first 4 terms of the Maclaurin series, including the terms that happened to be 0. So there is a whole bunch of Maclaurin series calculations. I'll catch you later.